Cambridge AS Computer Science, Chapter 1, Information Representation, Part 4, Internal Coding of Sound. In the last session, we did internal coding of images, and we knew that there is what is called vector graphics, and there is what is called bitmap images. The other one is called bitmap images. Bitmap images are formed by pixels. Vector graphics is something else. With vector graphics, you install. You store. You store the commands to draw various shapes in vector graphics. In bitmap images, you store pixel values. Internal coding of sound is something very, very similar to pixels in pictures. So sound is analog. Sound is analog. In order to store it on a computer, you need to convert it into digital. And this is done by sampling, recording. So internal coding of sound is analog and needs to be converted to digital to be stored on the computer. The amplitude, this is the amplitude. So the original wave should have been a smooth sine wave. However, those staircase appeared because of sampling, and there is what is called quantization error. We will see now how sampling will convert the analog wave into a digital wave. The amplitude is recorded as a set number of times. So you are not recording the signal at all the times, because otherwise it would be infinity. The signal is continuous. So you need to take samples. So the signal is a sound is analog and needs to be converted to digital to be stored on the computer. The amplitude is recorded a set number of times a second, and we call this sampling rate. This is something like image resolution in pictures. Okay? Each sample of an amplitude is giving a corresponding binary value. Eventually, every sample of these will be given a binary number. And again, this will be the bit depth. This will be the bit depth, just exactly like in pictures, because the bit depth is the number of bits given to a pixel in a picture. Also here, the bit depth is the number of bits given to a sample in sound. So they are the same. And we will multiply and divide exactly like pictures. Okay, so the binary number of each amplitude is saved in a sequence. So your file will be sequence of amplitudes. Those represent two samples, and then eventually they can be reconstructed again to give again the original audio. So for that particular example, for CD audio has 44,100 samples per second, and this is very high because with CD quality, we want the recorded sound to be of very high quality. Okay? And also for this particular example, each sample is given 12 bits. This is also very high. We will look at these examples very soon. Sampling, you need to know the definition of sampling, the effect of increasing the sampling rate, the definition of bit depth, the effect of increasing the bit depth. This is actually exactly the same like in pictures. When you increase the number of pixels, the image quality increases. However, the file size also increases. So sampling is defined as recording the amplitude of the analog sound wave at regular set interval. The height or amplitude of the sound wave is recorded at set time interval to get an approximation. This is an approximation, those staircases, and the difference will be called sampling quantization error. The difference will be called quantization error. This approximation of the sound samples are then encoded as a sequence of binary numbers and converted to a digital signal. Sampling rate. Sampling rate is the number of samples taken per second. The number of samples per second. Increasing the sampling rate will improve the accuracy of the recording. Again, sampling rate is the number of times the amplitude of the analog wave is taken per second. Higher sampling rate results in more accurate digital representation. Increasing the sample rate improves precision of the sound recording. There are smaller gaps. There are smaller gaps in the sound wave, as sound is recorded more often. Digital waveform is closer to the analog waveform. The quantization errors are smaller. Okay, okay. That was about sampling and sampling rate. What about sampling resolution or bit depth? Is the number of bits allocated for each sample. For example, each sample would be recorded in 8 bits or in 16 bits. And this will result in higher file size and better quality. The sampling resolution is defined as the number of bits used to store each sample. Sampling resolution is the number of distinct values available. Okay, so if you have higher sampling resolution, differences between those stairs will be smaller and will be closer to the original. Okay, so again, everything is written twice. This is specified by number of bits used to store each sample and referred as bit depth. The higher the sampling resolution, the smaller the quantization error. Higher sampling resolution results in less distortion of the sound. Bit depth is usually 8 bits, 16 bit, 24, or even 32 bits per sample. Okay, increasing the sample resolution will improve precision of the recording as there are more bits per sample and a wider range of amplitude of sound can be stored. Each binary amplitude in the digital is closer to the analog amplitude. Okay, quantization errors are small. Okay, so this is an example. Suppose a CD is being produced to contain a number of music tracks. Each piece of music is sampled at 44,100 sample per second. And this is the example I talked about for the CD quality. Each sample is 16 bits. Since the music is stereo, this will be multiplied by 2 because we have a right and left sound tracks. The above information mean 44,100 by 16 by 1. This is the number of bits per second. ماشي? But the number 2 is used to account for sound being in stereo. 1 byte is 8 bits. You may need to divide this by 8 to have bytes per second rather than bits per second. Sound encoding decision. In practice, for coding sound, two decisions have to be made. The number of bits to be used to store the amplitude and the number of samples. These are the two decisions. How many samples to be taken per second and the number of bits that will be used to store each sample. And definitely we will multiply them. Okay? Okay, everything here is repeated. 16-bit sampling. 16-bit is sufficient for good quality. 16 is very high. 16-bit sampling is very high. Gives you a very good dynamic range. Okay, almost gives you the maximum dynamic range the human ear can respond to, and is measured here in dB. dB is decimal. Okay. Okay, let us go to a practical example taken from the past paper. The following information refers to a music track being recorded on a CD. Music is sampled 44,100 times per second. Each sample is 16 bits. Each track requires sampling for left and right speakers. Okay? The number of bytes required to store 1 second of sampling will be 44,100 multiplied by 16, because this is the number of bits per sample, multiplied by 2 because this is stereo sound where you have left and right speakers. All divided by 8 because I would like the result to be in the form of bytes, not bits. Again, you have to find your way making that calculation without a calculator. If a particular track has 4 minutes, this is going to be multiplied by 4. If you like it in megabytes, you divide in MB. And if you like it in MB bytes, you have to divide by 1024 twice. Okay? Okay, please train yourself to go through these calculations without a calculator. Maybe leaving the formula like this will be sufficient. It depends on the question. Maybe asks for the formula and the answer is not important. Or if the formula is for 2 marks, the answer, the final result of calculation will be for 1 mark. Okay, let us read this. Changing the sampling rate from 40 kilohertz to 60 kilohertz, the accuracy increases. Changing the duration of recording from 20 minutes to 40 minutes, accuracy does not change. Changing the sample resolution from 24 to 16, reduction, the accuracy decreases. Okay, so that was about encoding of sound. Then the last topic will be compression. The last topic will be compression. So, as they can see, audio can result in a very big file, and pictures can result in a very big file. So, we may think of reducing the file size. The easiest way to do compression is using lossy compression. With lossy compression, for example, you reduce the number of samples per second. You reduce the number of bits allocated for each sample. However, by doing this, you are losing some of the details of the audio or some of the details of the picture, and those details will be lost forever. This is what is called lossy compression. So with lossy compression, you reduce the number of pixels, you reduce the number of bits per pixel, which will reduce the number of colors. With audio, you reduce the number of sample per second or the number of bits per second, and then you will have higher quantization error. Okay, maybe you have some margins of lossy compression that will not be noticeable by the human eye or not noticeable by the human ear because they are not perfect. Okay, so this is what is called lossy compression. Sometimes we need to do lossless compression. With lossless compression, the file after decompressing must be exactly identical to the original. This is very necessary when you are compressing data files or when you are compressing a program where nothing can be discarded. Pictures and sound, on video, you may do lossy compression because the human ear and the human eyes are not perfect. But if you are compressing a data file that consists of numbers that will be open in a spreadsheet program, if you would like to do compression, it has to be lossless. You reduce the file size without discarding any details. And this is really strange. It is quite straightforward that you discard some details and the file size reduces. However, how can you reduce the file size without discarding any details? This will be explained very soon with lossless compression. Let us first look at the topic from the beginning. There are two categories of compression. The first is lossy compression, and the file size is reduced with some loss of information, and the original file can never be recovered. The second is lossless compression, where the file size is reduced, but no information is lost, and when necessary, the process can be reversed to recreate the original file. Why do you need compression? Data files are very large and would take longer time to send the uncompressed file. So if you are sending a file by email, there is a limitation on the file size. So maybe you need to reduce the file size and then maybe you need to do compression. When you are uploading or downloading videos or audio or pictures, it will take very long time. So maybe you would like to reduce file sizes by using compression. Higher bandwidth, especially if you are uploading or downloading through the internet, you will need a higher bandwidth. Higher bandwidth will be needed to represent the uncompressed file. Compressed file will download and upload faster. Okay, so that was an introduction about the necessity for doing compression. Then we come to lossy compression. Lossy compression is very easy. Just discard some of the information. And the file is reduced deeply because if reduce the resolution, so number of bits multiplied by number of height, the number of bits wide, number of pixels wide multiplied by number of pixels high. If you reduce this because of multiplication, you are eliminating lots of data. And maybe the picture still the same, looks the same because of the human eye is not perfect. Lossy compression coding techniques cause some information to be lost, so the exact original file cannot be recovered in subsequent decoding. Decoding means decompression. Lossy compression of sound. Lossy technique make decision about what part of sound are important and discards other information. Lossy compression only keeps sounds human ear can process and discards sounds most likely people cannot hear. Lossy compression can reduce about 90%. And this is very obvious in MP3. An example would be MP3 compression. This is a very popular file formatting for distributing audio in a lossy way. It's still of very good quality. Not exactly the original, but you're enjoying. Sometimes on YouTube, you intentionally reduce the quality to save bandwidth. MP3 compression for audio, MP3 is lossy compression. It uses psychoacoustic modeling. It studies the shape of the ear and perceptual music shaping. certain parts of the music can be eliminated without significantly degrading the quality. MP3 compression removes parts of audio that human ears cannot hear. Advantage of using lossy compression. Why would you ever use lossy? As long as you have lossless. Lossy reduces the file more. So you may have a reduction of like 90% reduction. And the quality may still look the same, especially with images and sound where it is not necessary to have exactly the original soundtrack or the picture to enjoy. Okay, so lossy compression creates a smaller file. If you do lossless, it will not be that much reduced. Recording of a concert is a large file. So you are recording a concert, and then the length of duration, the duration of time is maybe 1 hour. So the file is really large. If you do lossy compression on the recording of the concert, you will save a lot. Okay, and needs significant reduction. Lossy compression remove details which can be lost without people noticing. So it is very clever because it only removes details that people will not notice at all. Okay, and the reduction in sound quality will not be noticed. Okay, lossy compression of images is the same. An image have some detail that could be removed. So let me give you an example. If you have a very high resolution image that is high definition, high definition, they call it 5K or something, which pixel is taking 5,000 pixels wide by 5,000 pixels high. And this can only be displayed on a very large television. If you are viewing that on your mobile phone, probably you don't have a space to display that huge details. If you do lossy compression on images, you will not notice because that high quality is above the capability of your mobile screen. Okay, so lossy compression can be used when an image can have some of the details being removed. Okay, the human eye can hardly notice. Okay, reduce the color depth. You reduce the number of colors. Instead of being 16 million color per pixel, just reduce that. Okay, JPEG is a compressed file format for pictures. Okay, that is enough about lossy. Let us go to that new strange thing, because it is really strange how you can do lossless compression, how you can reduce the file size without loss of any quality. We will do some form of statistics, some form of replacement. We will see how lossless compression may work. Lossless compression will allow subsequent decoding to recreate exactly the original. So with lossless, after decoding or decompression, you get exactly the original without any change of a single bit. This is very essential when you are dealing with text files, because text files have characters encoded in ASCII or numeric values or a program. If one bit is changed, the whole file will be corrupt. So it is really necessary sometimes to do lossless compression. Lossless compression is designed to lose none of the original detail and allows original files to be recreated exactly. However, lossless techniques can only achieve 50% reduction. Lossy can achieve 90% reduction. So it is only left with 10%. So with lossy, you only have 10% of the file, and it is almost the same. With lossless, you can only just get half of the size. at most, if possible. What is FLAC file? FLAC file is an audio file compressed in free lossless audio codec FLAC. Sometimes the original track for distributed, you want to have it lossless, which is an open source lossless audio compression. It is similar to MP3, however, it compresses without any loss of quality or any digital audio data. So this is FLAC file in contrast to MP3 file. MP3 is lossy, FLAC is lossless. Okay, how can we do lossless compression? Let us focus on text, because text needs to be compressed in a lossless form. With something called Huffman coding. Analysis is carried out to find the most often used characters. These are given shorter codes. So in English, for example, the E is used most often. So we give it a very short code. The T is also used very often. We give it a very short code. O and H, not as much. Other letters will be given longer codes. And on the average, the file size will decrease. So this is a form of replacement. Lossless compression relies on a form of replacement. You replace a code with a shorter code. Why? Because that is appearing quite often, and on the average, the file size will be reduced. This is what is called Huffman coding. Then comes the very popular run length encoding technique, and it is a lossless technique as well. So RLE is run length encoding. Please study it very well because it appears quite often in exams. Why do people like telephone numbers with similar running digits? What do I mean? If you have, for example, your telephone number or some data that is 000 1111 2222, you can see that you have similar numbers in a run. What is meant by in a run? Following each other. I have 6 twos following each other. So I don't need to tell you two. I can just say for you 6 successive twos or just 6 twos. So with run length encoding, what is a run? The number of repetition. Sometimes when the data have very long runs, like similar characters are repeated, so instead of putting the actual value, that is 2, followed by another 2, followed by another 2, I say 6 twos and 3 threes. So the encoding will be like this: 3 zeros, 4 ones, 6 twos, 3 threes, and definitely this will be shorter than the original. This is called run length encoding. With run length encoding, you mention the character or the digit, or how many, and then how many times it is repeated. And this, on the average, will increase or would increase the file size if the file has lots of similarities. Sometimes when the file doesn't have any similarities, run length encoding will increase rather than decrease the file size. So this is in principle how run length encoding is used, and this is the most popular form of lossless compression. The point is, when you picture a wall, for example, you will find that all pixels are similar because large areas of the wall have the same color, if it is like that. So in that case, lossless compression will be helpful as well, and it is lossless. So when you convert back When you convert back, you get exactly the original message without any loss of details. So this is how lossless compression would work. Let us read what is written here for run length encoding. A different lossless compression technique rather than Huffman coding. Huffman coding is not that popular in exams. Run length encoding is very popular in exams. Okay, is run length encoding RLE. The compression converts sequences of the same bit pattern into code that define the bit pattern and the number of times it is repeated. So the value and the number of repetition. For example, the data 000 will be 3 zeros. 11111 will be 4 ones. 2222 will be 6 twos. Okay, and so on. Run length encoding is lossless. Is a lossless method of compression. It reduces the physical size of a stream of adjacent identical characters or pixels or bytes. Okay? The repeating string, this is the run, is encoded into two places. One value represents the number of identical characters in the run count. The other value is the code of the character itself. So we have the run count and the run value. The run value and run count combined may be preceded by a control character. Example, and that example definitely is taken from your classifier. The following diagram shows the binary color code that represent each color. So black is represented by 153 and white is represented by 255. And these values are in binary. If you have a picture like this, this is a picture. This is a picture. You have 16 pixels wide and 95 pixels high. Okay? RLE will compress the first 3 rows of this image. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 of 153 because 153 is the code for blue or black. 153 is for B and black. And then followed by 1, 2, 3. So 255 of 3 times. And again 153 3 times. So it is 10B and then 3W and then 3B. This will significantly reduce the file size. Instead of writing B, then B, then B, then B, it is just common or normal that you say 153 10 times. And if you decompress or decode, it comes exactly like the original because there is no loss. Lossless compression relies on some form of replacement, and this is replacement. Again, this line, you have 9 times 153, followed by 6 times 255, followed by 1 time of 153. That is the blue. The last line, see, the last line is even compressed in a better way because it have 7 153 followed by 9 255. Okay, so with that example, we come to the end of explanation of chapter 1 about internal encoding, about information representation. The last thing we did right now was lossy and lossless compression. I hope everything is clear. Thank you so much for your attention.